Hey all. All right. So yesterday I talked about the couple of problems that had to do with optimization. Today I'm going to do a couple of little different examples that a little more complexity to them, but I think are handleable, manageable for the area problem, for instance, in particular. Let me show you an example that they gave in the text. And take a look at this with me, if you would. All right, if you can see it down here, I'll try to zoom in on that just a little bit and see if I can get that a little bigger. But I think it should be pretty clear. I don't want to distort anything here. Okay, so here's the problem that we're talking about. Right here, it starts, yeah, this example right here. And the picture, the diagram they've got is right over here. And it's showing that the problem reads, a farmer has 4,000 meters of fencing, wants to include a rectangular plot that borders a straight river. River here, plot here, all right? And if the farmer does not fence the side along the river, what's the largest rectangular area that can be enclosed is the question. So we're trying to maximize the largest rectangular area, maximize area. So we've got two situations. We've got an amount of fencing, which has really got to do with the perimeter of the area. And we've got the area itself, which we're trying to maximize. So what we've got two equations on this. The problem's written here. So I'll draw the diagram, put it on a little bit of a picture here, and see if we can't get a problem solving moment underway. So let's look at this. Here's what I've got. I've got let me move over to looking at my iPad. It'll just take a second for it to pop up. Okay, so we've got the river there, and we've got two sides, and one of the sides along the river we're not going to fence. So the variables they had picked in that diagram were X on these sides, and they picked Y here. How much fencing was there? They said 4,000 meters of fencing, 4,000 meters of the outside. So that means that the two X's plus the Y together equals fencing. You know, if I had originally started the problem, I would have said probably 2X plus Y equals F. That's for the fencing. When 2X plus Y then equals 4,000. That's a constraint we've got that we're working with. That's not what we're trying to maximize. We're trying to maximize the area. The question was, the way the question was posted was, what is the maximum area that can be used for this amount of fencing? So the idea is the area of this region right in here, this area of this region is going to be equal to length times width, which is X times Y. All right, so in the simplistic problem, so this is the function we're trying to maximize. So we're going to take the derivative of this and set it equal to 0. But right now it's in terms of X and Y. So what we're going to do is get that to be just in terms of X would be the goal of my situation. And either that or of Y. And Y is already by itself in our function. X has got a 2 in it. That makes it a little more complicated. Unless we can just solve for Y right now. So in this problem, we end up with Y equals 4,000 minus 2X. And now if I substitute the Y in here, I'll have a function that's just in terms of X. I can take the derivative, set it equal to 0, and solve for the X that will give us the value we hope for. Remember, X isn't the value we want. We want what is the maximum area was the original question. So we've got to use X, figure out what Y is, and then come up with the answer. So you got to make sure you remember it. Area is what you're looking for. This is what the end result is. So let's substitute in, and we end up with area equals X times 4,000 minus 2X, which gives us 4,000X minus 2X squared. So we've got our equation now, area, just in terms of X. We could just say A of X if you wanted to. That would be a good representation of it. A of X equals 4,000X minus 2X squared. So if we take, that is the function we're trying to maximize. And Now, so it means we take the derivative, set it equal to 0, and see what the result is. Notice the shape of this graph. Notice what the polynomial is we've got. We've got minus 2x squared, right? What's the shape of that? That's a parabola, right? Upside down, the graph looks like this. Maximum happens where? Right there. That's where the slope is equal to 0. So take the derivative, set it equal to 0, and you can figure out what the x is, and then we can go from there. So a prime of x is equal to 4,000 minus 4x, right? All right, yes. All right, and that equals, that is the derivative, equals 4,000 minus 4x. And if we set that equal to 0, the derivative equal to 0, we'll find where the slope is equal to 0. It's a minus sign. So we've got a minus there, so I'm going to take that across to the other side, equals 4,000. And as a result, we end up with x equals 1,000. So when x is equal to 1,000, we have the max area, but that doesn't give us what the actual value. We want the area. So if you notice, remember what we did last time, one of the functions we had to solve for y to do the substitution. So if I bring the y down here, I get y equals 4,000 minus 2, and the x is 1,000. I substitute that in. I end up with 4,000 minus 2,000, which is 2,000. So y is equal to 2,000, x is equal to 1,000. So the area question that we had was equal to x times y. Now I could have plugged it back into my my equation, just had x in it, but I can plug it back in here as well and get 1,000 times 2,000, which is equal to 2 and 6 zeros. So it ends up being 2 million, right? And think about the units. What is this? Is this all in feet? Meters. It's in meters. So we end up with 2 million meters squared. So it equals the max area. All right. That's the logic of the problem, the situation. And notice what we did. We came up with an equation that described what was given, the information that we got a certain amount of fencing. We had to come up with an equation for that. That's that situation right there. And then we were given the actual amount of fencing that we had, so we ended up with that scenario. We were able to solve for y. And as a result of substituting back into what the equation we're trying to maximize, which was the area of that region, the area of that situation, we substitute the y in for that, we end up with our equation in terms of x. That we could take the derivative of, set it equal to 0, solve for x, get y, answer the question. Max area is 2 million meters squared. All right, that's one practice problem. All right, thank you. And we'll move on to another question in just a little bit.